All right, so a video over um, basically the first couple steps of a stoichiometry problem. And to make things simple, I'm just going to kind of show you those steps. Like, I'm not going to put a full stoic problem. I'm just going to basically put up like kind of um, what you should do when you're tasked with a stoic problem. So, if that's a bit vague, let me start, I guess, typing it, and maybe it'll make more sense. So, or maybe I don't know. Maybe for the sake of argument, maybe I will put a full stoic problem, just so you can kind of see it, and a simple one. Okay. So if I said something like, let's do calcium. I don't know, calcium phosphide reacts with oxygen gas in a single replacement reaction, right? There's no grams listed in here, okay? So just for sake of argument, let's say I said, I don't know, 120 grams of calcium phosphide reacts with, let's say, I don't know, 43.2 grams of oxygen gas, okay? This video is not going to talk about the grams, so that's why I was kind of thinking maybe I wouldn't, but, we'll just go with it. We'll make it work, okay? How do you do this problem? Well, in order to even have a chance of doing it, you have to know how to make calcium phosphide, what oxygen gas is, what a single replacement reaction is, and then you need to know how to balance that chemical reaction. Okay, so to do this, let me switch over to the pencil, right, or the drawing tool, I suppose, is you're going to need to figure out what is calcium phosphide. And to do that, what you're really going to want to, oh, there's my mouse, move that over. Oh, wait, this is upside down, that's why. I was like, wait a second. Wait a minute. There we go, that's a lot better. So for calcium, right, you say, calcium, I look in the periodic table, that's Ca, and I say, yeah, that's calcium. And then phosphide, it ends in "ide," which generally speaking, there's like one or two exceptions to this, means it's going to be just an element in its anionic form. Recall that cations are positively charged, anions are negatively charged. Okay, so phosphide, you say it's probably an element. In this case, it is. You say, what does phosphide sound like? It sounds like phosphorus, because this is the anionic form of phosphorus. So I'm like, okay, it's calcium and phosphorus, right? If you just wrote this, this would be wrong, because you need to know what the charges of the calcium are, or the calcium is, and the charge of what phosphide will be. Okay, and to do this, you could use like a periodic table that has charges included. Okay, depending on what class you're in, you might have like an ion sheet as well. All right, but in this case, this one's pretty easy because calcium is a alkaline earth metal. Alkaline earth metals are always going to have a +2 charge. Okay, this is just like ionic compound formation, which I made a video on, so you're probably like, I remember this, hopefully. Okay, but it helps to see the steps. So that's +2. Phosphide is P with a -3 charge. You might say, well, wait, I look at my periodic table and mine says that phosphorus can also have a charge of +3 and +5. It can, but that's more of when it's in a covalent compound, and that's what's called its oxidation state, which is a little bit different, okay? For these kind of problems, to make things simple, we are working with ionic compounds, which means I need a cation and an anion. Okay, so calcium has to be positive. It's a metal. Calcium is never going to be negative. Okay, whereas phosphorus, because there's other nonmetals that are more electronegative, it could behave. Keyword is behave, not literally behave like a cation. Okay, but don't worry about that. Worry about the fact that, hey, it's going to be negative. Okay, in this case. So P3 minus. And again, I made a video about ionic compound formation. We can do our crisscross method to save time. So what does that look like? We would have Ca3P2. Okay, that's calcium phosphide. This right here is the same thing as calcium phosphide. That's the formula for calcium phosphide. Okay, this is not the answer. This is not done. This is just literally the first step of many. Okay, so then you got to say, okay, it's reacting with oxygen gas. When it says oxygen gas, the assumption here is that this is oxygen in what's called its allotropic form, I should say, which is a fancy way of saying how it typically manifests, how we would typically find it. So how do we typically find oxygen? As oxygen gas, aka O2. Okay, this is the same thing as an oxygen molecule double bonded to itself. Okay, remember Lewis structures. This would be oxygen gas, O2. Okay, oxygen is one of the 7 atoms, the 7 elements, I should say, that are, when they're by themselves, they will be what's called diatomic, which just means 2 atoms bonded together. Okay, those 7, as a reminder, the beautiful thing about this is that you think the number 7 and you immediately go to nitrogen. Oh, wait, I did it the wrong way. You go to nitrogen. Aha, yeah, there we go. And nitrogen is number 7. So you say, oh, and then you make a number 7. So what you do, let's see if I can do this without, there we go. You go to nitrogen and then oxygen and then fluorine, and then we go down. It makes a number 7. Down to chlorine, and then below chlorine is bromine, and then below bromine is iodine. That makes a number 7. And then you might say, well, wait a second, that's only 6, right? Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, that's only 6. And then the last one, number 7, is hydrogen, which is kind of by himself up here, right? He's up here by himself for a reason. Okay, that's the way you can think about it. What does it mean if you have them by themselves? It's got to be H2, Br2, I2, Cl2, F2, O2, N2. Okay, that's what it means. So that's that. So those are your reactants. Yay. And now this is a single replacement reaction, which simply means what? Somebody is getting kicked out of this molecule. Okay, the oxygen is quote unquote by himself. He's single and he's looking to mingle. So what happens? He's going to kick somebody out. Okay, who is he going to kick out? Well, he can only kick out the phosphorus. Okay, he can't kick out the calcium because the calcium is going to give up his electrons way more readily than the phosphorus would to the oxygen. So basically what's going to happen here is the phosphorus is going to get replaced. The oxygen is more eager to take these electrons, is how you can think about it. Okay, and truthfully, any reaction can reverse. So we could write this reaction backwards and it would still work. All right, it's a question then if it's endothermic or exothermic, but we're not there yet. That's later, okay? But for right now, you say, okay, I kind of get that. What does it mean, though? I'm going to switch colors just so you can kind of picture this. It means that the phosphorus is going to get kicked out by the oxygen, which means what's going to happen? We're going to have a calcium still. He's going to have a +2 charge, has not changed, okay? And now we have an oxygen molecule with a -2 charge. How do I know that? It's a chalcogen. Chalcogens have a -2 charge. It's also on your periodic table. Notice the 2 down here is not there anymore. You might say, oh, is it up here now? They're different things. Remember, the numbers below, the subscripts, are how many of those atoms are in that molecule. The number above, as a superscript, is the charge. In this case, oxygen has 2 extra electrons. Okay, we can do our crisscross. When you do crisscross, reminder, you have to say, is it simplified? Can I simplify Ca2O2? Because if you just did this the way, with the shortcut, if you just did this, you might write this down as the answer, and that would be incorrect. You need to simplify it. So simplifying 2 and 2 is simply 1 and 1. So I'm going to have CaO, calcium oxide. Okay, who's left over? Who's now single? The phosphorus. Okay, you might say, oh, it's P2, it's going to be P2 again. No, it's just going to be P. Phosphorus does not bond with itself, at least. And again, you got to realize things can get messy, but we make the assumption, in this case, that it's not going to be P2. Okay, if it was H, it'd be H2. If it was Br, it'd be Br2. If it was N, it'd be N2. But it's not one of those 7. So we say, okay, it's just going to be by itself, it's going to be P. Okay, so this is the correct formation of the products. Okay, you've given me the reactants over here, and you've formed the products. And now you can balance. And for balancing it, we need to think the number of atoms on both sides has to be the same. Not just the number of atoms, period, but the number and type of atoms has to be the same. The elements, that is, have to be the same. So my recommendation is to tally out. You don't have to do this, but it might help you, is to tally out what we have. So we have calcium, we have phosphorus, and we have oxygen, right? Those are the 3 elements. And then the same thing on this side, right? Calcium, phosphorus, and oxygen. Okay, and again, you don't need to do this every time, but it'll help you if you're new to this, right? How many calciums? 3. How many phosphorus is 2? How many oxygens? 2 on the reagent side. On the product side, we only have 1 calcium, we only have 1 phosphorus, and we only have 1 oxygen. Okay, so we need to get all of these balanced. And balancing is something that you have to practice. You can't just do it once and say, I'm an expert, because you really need to see it a bunch of times and get a feel for it. I wish there was a magic way to do it. There really isn't. There is a way you could do it with a system of equations, but I would argue that's way more complex to learn, especially if you're not math inclined, than just doing it the methodology that's how it's often taught, which is pick one and try to make it work around that. Okay. What does this mean? It means you pick one and you say, I'm going to try to get that balance first, and then try to see if the other ones can balance around that. So in this case, any of them is going to work, right? But I might recommend picking ones where there's like one by its. So when there's one in a molecule, I might focus on that one first. When you have like bigger prime numbers, I might focus on that one first. Different methodologies, different systems that can work in different types of problems. Okay, there's no magic bullet that works every time, if that makes any sense. Okay, so what I'm going to do is I'm going to focus on the oxygen first, because there's only one here and there's two over here. So I say I got to get this to at least be 2. So what I'm going to do is I'm going to put a 2 in front. When you balance a chemical reaction, you can only put coefficients in. You cannot change the subscripts, because that would change the molecule, and we can't do that. Okay, so I put a 2 here, and this means what? Now I have 2 oxygens, yay, because there's 2, it distributes in, but that also means now there's 2 calciums. Okay, and you might say, okay, well, is that good or bad? Well, I have 3 calciums over here, right? So you're like, oh, which means it can't be 2, okay? And if you're like, wait, does that mean we're wrong? Yeah, it means it can't be 2, right? And I'm kind of deliberately showing it to you this way to say this happens and that's okay. Like, that's not a problem because we can easily fix it, okay? So if you do this and you say, oh man, I picked the wrong one, perfectly fine. All you got to do is basically erase it and try again. So then I say, okay, you know what, maybe the calcium is where I want to start. So maybe I say, let's put a 3 there. If you put a 3 there, though, so I'll do it just to prove a point to you, right? If I put the 3 there, oh, it's an eraser now. Hang on, I switched it. I'm trying to be fancy with my pen, and I ended up, where'd it go? Come on, where'd you go? Where'd you go? Oh, there you are. There you are, okay. If I put the 3 here, hopefully you're saying, I see the problem, because now I have 3 oxygens, but this is 2, and no integer times 2 gives me 3. I can't put 1.5. I can only put integers when I'm balancing. Okay, whole numbers. So you say, okay, 3 is not going to work. So what do? I have to find a least common multiple of 2 and 3, which hopefully you're going to say, oh, that's 6. Okay, so I need to get 6 calciums. So I can put a 6 here. Okay, I put a 6 here. So the calciums are now 6. The oxygens are now 6. And if you're like, how is this making things better? Because on this side, I can get that to be 6, and I can also get the calciums to be 6. So for calciums, there's 3 of them here. If I put a 2 in front, that distributes in. 2 times 3 is 6. That's good. And then for oxygens, to get 6, all I got to do is put a 3 here. Right? 3 times 2 is 6. So that fixes that. You can see how that right there, I got 2 of them done. And now I have one more, which is the phosphorus. When an element is by itself, that's good, because I can usually do that one last, because it's like I can just put whatever number I need, I can put it there. If there's a 7 needed, if there's a 9 needed, a 3, a 1, whatever, it's a good one to do last, if it makes sense, when it's by itself like that. So I say, how many phosphoruses do I have? When I put the 2 in front here, that's 6 calciums, and now I have how many phosphoruses? 2 times 2 is 4. So how do I get 4 over here? Easy. We put a 4 in front of that, okay? And that makes it 4, okay? And then you ask yourself, hey, is everything balanced? And the answer, as you can see, is indeed it is. The last thing to do is just to make sure these numbers, these coefficients, I should say, make sure you can't simplify them any, okay? Just like with ionic compounds, if I had 4, 4, 4, I could simplify that to 1, 1, 1. If I had 10, 5, 5, I could simplify that to 2, 1, 1, okay? 2, 3, 6, and 4, I cannot simplify that. Okay, 2, 3, 6, and 4, there's no way to simplify it. I can't divide it by 2 because it doesn't go into 3. I can't divide it by 3 because 3 doesn't go into 2, or 4 for that matter. Okay, so this is the simplest, this is a simplification, or that's not the right word. This is the simplest form of the reaction. Just to prove a point to you, if I made this 4, this would have to be 6, and this would have to be 12, and this would have to be 8. Would that work? It would, right? Just prove it. 4 times 3 is 12. 12 times 1 is 12. 4 times 2 is 8. Hey, that's 8 over here. 6 times 2 is 12. 12. I'm sorry, I keep looking at this one. This is the 12, right? 12 times 1 is 12. It works. Okay, and this is actually going to be the reason we're doing this, because when you get to stoichiometry, that ratio is what matters. And we ideally want the simplest ratio. 6 to 2 is the same thing as 3 to 1. So that's better to write 3 to 1 than 6 to 2, if that makes sense. Right? 8 to 2, it's better to say 4 to 1 than it is to say 8 to 2, if that makes any sense. Okay? So I'm going to I think pause, we'll finish this video here. I think I'll make maybe 1 or 2 more going over this, just because I know it is a little hard, and seeing it being explained and talked through is hopefully helpful to you, okay? But I really can't stress enough, you have to practice this yourself. You really can't just watch somebody do it and go, oh, I get it. It's like riding a bicycle. You can't watch somebody do it, you have to do it yourself, okay? So anyway, have a great rest of your day, and yeah, hopefully this is starting to click for you, and you say, man, chemistry's fun. Hopefully. All right, have a good day.